Every single night you look up at the sky and you see stars, billions of them, and somewhere out there, statistically speaking, there are almost certainly other civilizations, maybe millions of them. So here is the question that should keep you up at night. Why hasn't a single one of them ever showed up here? Not a signal, not a probe, not even a postcard. Now, most people blame the distance, and yes, space is unimaginably big. But today, I want to go deeper than that, because the real answer is not just about distance, it is about the laws of physics themselves. And those laws, as Feynman once said, do not care about your plans. G'day, welcome to Curious Physics AU, the channel where we take the biggest questions in the universe and break them down so simply, even your Year 10 science teacher would be impressed. I'm Abdullah, and today we are doing something special. We are going to think about interstellar travel the way Richard Feynman would, not with complicated maths on a board, but with honest, clear thinking. Because Feynman had this brilliant idea. He said, if you cannot explain something simply, you do not really understand it. So let's understand it. By the end of this video, you will know exactly why interstellar travel is not just difficult. It may be physically, fundamentally, and permanently impossible. And you will be able to explain it to anyone. Let's go. First, let's talk about scale. Because humans are genuinely terrible at understanding cosmic distances. You know how far away the moon is? About 384,000 kilometers. The Apollo astronauts got there in roughly 3 days. Now the sun? That is about 150 million kilometers away. Light, the fastest thing in the universe, takes about 8 minutes to get there. So far, so good. But now things get wild. The nearest star to our sun is Proxima Centauri. It is about 4.2 light years away. A light year is the distance light travels in an entire year, roughly 9.5 trillion kilometers. So Proxima Centauri is about 40 trillion kilometers from Earth. Now here is the gut punch. Our fastest ever spacecraft, the Voyager 1 probe, is traveling at about 17 kilometers per second. That is blisteringly fast, faster than anything humans have ever built. At that speed, to reach Proxima Centauri, it would take roughly 73,000 years. 73,000 years. And Proxima Centauri is our nearest neighbor. The Milky Way galaxy stretches for about 100,000 light years. The nearest large galaxy, Andromeda, is 2.5 million light years away. We are not just talking about a long trip. We are talking about distances so vast, the human brain literally cannot picture them. All right, so you might be thinking, okay, what if we just go faster? What if we build a ship that travels close to the speed of light? Fair question. Let's think about it like Feynman would. Light travels at about 300,000 kilometers per second. In 1 second, light can travel around the Earth 7.5 times. That is our universal speed limit. But here is where Einstein's special relativity gets absolutely mind-bending. As an object with mass accelerates towards the speed of light, something strange happens. The object gets heavier, not physically heavier like you after Christmas, but in terms of what physicists call relativistic mass. Here is a simple way to think about it. Imagine you are pushing a shopping trolley at Woolies. Easy, right? Now imagine the faster you push it, the heavier it gets. And the heavier it gets, the more energy you need to push it faster. And the faster it goes, the heavier it gets again. That cycle never ends. To actually reach the speed of light, you would need an infinite amount of energy. And last time I checked, we do not have infinite energy lying around. So the speed of light is not just a record waiting to be broken. It is a wall, a fundamental universe-enforced wall. Now, what about 10% of the speed of light, or even 1%? Surely we could manage that. Well, at 1% the speed of light, about 3,000 kilometers per second, a trip to Proxima Centauri would still take over 400 years. And the energy required to accelerate a reasonably sized spacecraft to that speed, using the best rocket technology we understand today, we would need more fuel than exists on Earth. That is not an engineering problem. That is a physics problem. Let me make this really concrete. This is the part Feynman would love. Imagine you have got a cricket ball, about 160 grams, standard size. Now imagine you want to accelerate that cricket ball to just 10% the speed of light, using Einstein's famous equation, E S mc2, and accounting for relativistic kinetic energy, the amount of energy required is roughly equivalent to, wait for about 25 times the total annual energy consumption of the entire planet Earth for a cricket ball. Now imagine doing that for a spacecraft, a real one, with life support, food, fuel, crew quarters, radiation shielding. We are talking hundreds of thousands of kilograms at minimum. The numbers become so large they stop making sense to the human brain. We are talking energy outputs that dwarf anything our civilization has ever produced or could produce in the foreseeable future. And this is not a technology gap. This is not like saying we just need better batteries. This is the universe telling us, in the language of mathematics, that moving large objects very fast costs an extraordinary, almost impossible amount of energy. There is a concept physicists use called the mass ratio problem. To accelerate a spacecraft using rocket propulsion, you need to carry your fuel with you. But fuel has mass. And that extra mass means you need even more fuel to move it, and that fuel has mass too. It is a brutal, self-defeating cycle, and it was identified by a Russian scientist named Konstantin Tsiolkovsky over 100 years ago. The rocket equation. It is merciless. So even if aliens exist, and the statistics say they very likely do, the physics of energy and acceleration makes crossing interstellar distances almost incomprehensibly difficult. Now here is where it gets genuinely weird. And this is pure Feynman territory, because this is where physics stops being intuitive and starts being extraordinary. Einstein's special relativity tells us something remarkable. As you travel faster, time slows down for you relative to someone standing still. This is called time dilation. And it is not science fiction, it is real. We have measured it with atomic clocks on aeroplanes. So imagine a crew of astronauts traveling at 99% the speed of light towards Proxima Centauri. For people back on Earth, the trip takes about 4.3 years. But for the crew on board, due to time dilation, they might only experience a few months. So in theory, an alien civilization could send a crew on a journey that feels like months to them, even if thousands of years pass back home. Sounds promising, right? But here is the catch Feynman would raise immediately. Where does the energy come from? Even at 99%, the speed of light, the energy required to accelerate a crewed spacecraft is absolutely staggering. The time dilation trick does not solve the energy problem. It only changes the experience of time for the travelers. And there is another brutal detail. Deceleration. You have to slow down again at the other end. That costs just as much energy as speeding up. Every single joule you spend accelerating on out, you need to spend again to stop. The universe charges full price, both ways. So now let's connect all of this to one of the most famous puzzles in all of science, the Fermi Paradox. In 1950, physicist Enrico Fermi was having lunch with colleagues and asked a deceptively simple question: where is everybody? If the universe is 13.8 billion years old, if there are hundreds of billions of stars in our galaxy alone, if many of them have planets, and if life has had billions of years to evolve and develop technology, where are all the aliens? The silence of the universe is one of the deepest mysteries in science, and the physics we just discussed gives us one very compelling answer. Not a comforting one, but an honest one. Interstellar travel might simply be too hard. Full stop. Even a civilization millions of years more advanced than us still has to obey the laws of physics. They cannot exceed the speed of light. They cannot conjure infinite energy. They cannot avoid the rocket equation. The universe might be absolutely teeming with life, intelligent, curious, perhaps even looking up at their sky right now wondering the same thing we are. And they are all stuck, just like us, separated by distances so vast that even at the edge of physical possibility, a journey between stars takes centuries or millennia. Feynman would say, nature does not owe us convenient distances. The universe was not designed for sightseeing. Now, to be fair, physics does tease us with some theoretical possibilities. Wormholes, predicted by general relativity, could theoretically connect two distant points in spacetime like a shortcut. Fold space, step through, arrive instantly. But here is the honest physics answer. We have never observed a wormhole. We do not know if they can exist at macroscopic scales, and theoretical models suggest keeping one open would require something called exotic matter with negative energy density, which we have also never observed. The Alcubierre warp drive, proposed in 1994, describes a way to compress space-time in front of a ship and expand it behind. Technically, the ship itself never exceeds the speed of light. Space moves around it. Beautifully clever. But the energy requirements calculated for even a small warp bubble are the mass energy equivalent of the planet Jupiter, converted entirely to energy. So, possible in theory, impossible in practice, at least with anything we understand today. And that is not a failure of imagination. That is physics being honest with us. So, let's bring it all together, the way Feynman would. Interstellar travel faces not one wall, but several. The tyranny of distance, the universal speed limit, the catastrophic energy requirements, the brutal rocket equation, and the cruel symmetry of having to decelerate at the other end. Any one of these alone would make the journey extraordinarily difficult. Together, they make it possibly the greatest challenge the laws of physics have ever presented to any civilization anywhere in the universe. Does that mean it is forever impossible? Feynman would say never in physics. The universe has surprised us before, but we should be honest about where the evidence points today. And to me, there is something beautiful about that. The universe is not a theme park. It does not bend its rules for the curious. But the fact that we can even ask these questions, that we can figure out the laws that govern stars and galaxies using maths and experiments here on Earth, that, as Feynman once said, is a kind of miracle. If you reckon physics is worth understanding, smash that subscribe button and join the Curious Physics AU community. New videos every week, built for Australian students and anyone who loves asking the big questions. Leave a comment below. Do you think interstellar travel will ever be possible? I want to know what you reckon, and I will see you in the next one. Catch ya.